Hello, everybody. Welcome to Ruby Rogues. Today on our panel, we have Luke Stutters.
Hi.
And we have Matt Smith.
Hello.
And I'm John Epperson. And today with us, we have a special guest. We have Takashi Kokubun. Did I pronounce that reasonably well?
Yeah.
Okay, sweet.
Hey folks, this is Charles Max Wood, and I just launched my book, The Max Coder's Guide to Finding Your Dream Developer Job. It's up on Amazon. We self-published it. I would love your support. If you want to go check it out, you can find it there, The Max Coder's Guide to Finding Your Dream Developer Job. Have a good one. Max out.
Takashi, would you mind telling us why you're famous, why people know about you?
So these days, I'm maintaining the feature of the Ruby called JIT compiler, which is abbreviation of just in time. And that's a feature to optimize the Ruby, the scripts itself. So instead of optimizing the Ruby virtual machine, which is interpreting the bytecode of the Ruby scripts, we also added another way to optimize the Ruby, and which is a way to optimize the bytecode into the native code and just calling the native code by the native machine. So because it can eliminate the way to run the virtual machine, like program counter on the stack pointer, which is just a virtual thing to the Ruby virtual machine, we, instead of using the VM registers to native registers, because we can use the native registers by the native code, we can optimize the Ruby code further by implementing the Ruby methods as a native machine code. We can now unblock many optimizations on the Ruby interpreter of the CRuby. So I've been implementing that for about 3 years now. Since Ruby 2.6, I introduced that feature. I've maintained that, and I've continued to optimize the JIT compiler further, and I sometimes talk at Ruby conferences about that. So I think I'm being known as a Ruby JIT compiler implemented.
Gotcha. And all of this is related to, I don't know if we're calling it 3x3 or 3x3, but basically trying to make Ruby 3.0 3 times faster or whatever goal.
I called it 3 times 3.
All right, there we go. I don't actually know the official thing for it, but it's all kind of related to that, right? Like we're busy trying to make Ruby faster.
Yeah.
Sweet. Can you tell us, where are we at on that? Maybe give us a little bit of a rough idea of where we are.
So the goal in detail is that Ruby 3 wants to be 3 times faster than Ruby 2.0. And because since Ruby 2.0, we added many optimizations in both VM and the JIT, we are at least faster than 2.6. 2.0, 2.7 is faster than 2.0. So when thinking about what times faster than 2.0, we need to think about which benchmark we are using. And there are multiple benchmarks to measure the performance between the latest Ruby and 2.0. And the first one is one called OptCarrot, which is just a NES emulator, Famicom emulator running on the Ruby interpreter. And that's not an actual production use case like REST applications or Sinatra or whatever web applications or middlewares written in Ruby. On the other hand, it's written or using purely running on the Ruby virtual machine. So it can measure the Ruby's pure performance at least, like not using the I/O or not memory intensive. So for OptCarrot, we've already achieved like 2.5 times faster in JIT compiler. And virtual machine is, I don't remember the number, but this JIT is making it significantly faster than virtual machine. So obviously JIT is a part of Ruby 3 times 3 faster thing, major strategy of it. But we are still not there for 3 times faster yet. Some of our experiments are achieving better performance at the JIT compiler. So I'm hoping, or at least I'm thinking possible that we can optimize up to the 3 times 3 faster using JIT compiler. But my other focus or my main goal of the JIT compiler is that we want to optimize actual production performance, like Rails application, for example, because in my company, we are running the Rails applications on production servers. And if Rails applications can run faster than other older Ruby versions or virtual machine, we can just turn on the JIT compiler to reduce the number of servers, for example, or improve the user's experience by reducing the latency of one single request. So it's instead of too much focusing on the opt-caret optimization, I switched gear to optimize the Rails or Sinatra or web applications instead. And in Ruby from 2.7 and in that 3.0 development, I'm currently focusing on such kind of web application benchmark improvement. And therefore, I'm in 2.7 or at 3.0, opt-caret performance are not so improved yet. But if I need to somehow achieve the goal for 3x3 faster thing, I maybe focus on opt-caret improvement, and then I think I can achieve that by focusing on what's slow in opt-caret instead of what's slow in Rails web applications.
So the opt-caret is a Nintendo emulator for playing games. I think it came out about 2011 kind of time, correct?
I don't remember, but kind of.
It's getting on to 10 years old, I think. And that was kind of the same time as Ruby 2, yes? Mm-hmm. So the 3x3 goal is to make Ruby 3 times faster than it was in Ruby 2.
Yeah.
And it's getting there, but I've seen a few talks, and I think the consensus is to get it 3 times faster, then we do have to make a kind of big change, correct?
Yeah,
this is my feeling. I'm sure it's your feeling as well. So the JIT is one major change we can make. And I was just on the opt-caret GitHub, and if you look on the opt-caret GitHub, it has a graph, and Ruby 2 is benchmarked at 26 frames per second, and the latest MJIT comes in at nearly 49. So I think it's safe to say you've got a 2 times increase already, correct?
Yeah, I think so.
But the same performance improvement you don't get the same speed up when you start using MJIT with Rails. How does it behave with simpler systems like Sinatra?
So situations are a little bit similar to Rails in Sinatra. Actually, I have a benchmark using Sinatra, but it's a little bit too simple, but still having the same kind of impact on the performance with JIT compiler. So to explain the background, I need to explain what's going on behind it first. So when we run opt-caret, the opt-caret benchmark parameter is to run the NES emulator for 180 or 60 frames per second. Frames for emulating the one single game, and it runs for some seconds or tens of seconds, and it doesn't run for a long time. At the same time, we need to JIT compile the Ruby methods to native code, and because JIT compiler of the Ruby 2.6 or later versions are using C compiler to generate the native code from the Ruby methods, we need to wait for the JIT compiler to finish generating the native code. And it takes about, when the method is simple, it takes about 200 or 500 milliseconds. And because NES emulator finishes us a little bit quickly for running the 180 frames, compile a lot of methods, and it can, I think in my computer, it compiles like 20 methods during the benchmark. And so it can optimize only 20 methods during the benchmark. And on the other hand, in web application benchmarks, I'm running the Sinatra or Rails for a while, because in actual production performance, we run the application for a while, and the long-term or long-running version or the performance after waiting for a while is more important than just the startup performance, because it's the dominating the performance of the actual server situation. So I wait for compiling all the methods before actually measuring the performance in the Sinatra or else. And in actually, this is sort of impacting that in a bad way and also in a good way. One thing in a bad way is that when we are running the C compiler, it consumes some resources like CPU resources and memory. And because CPU caches are shared between cores, at least in the last level cache in a usual CPU cores, it somehow impacts this compiler impacts the actual Ruby interpreter performance as well. So it's usually generally faster when JIT compiler is not running. And so if we wait for JIT compiler to finish compiling the methods, it's generally faster. But on the other hand, waiting for JIT compilation means to finish compiling all the methods. And in Ruby 2.6, the number of methods to be cached at maximum was 1,000 methods. But since Ruby 2.7, we changed the default value to 100. So when we wait after the JIT compilation, there are 100 methods which are already native code. And when we compile such kind of lot of methods, it becomes slower by another reason, which is CPU cache size. Because the CPU cache size is very limited, so there are multiple levels of CPU caches in the CPU, like level 1 L1 cache, which is a little bit smaller than all other level caches, and level 2 and level 3. And I don't remember the exact numbers, but even in the last level cache, usually level 2 or 3, which is usually some tens or hundreds of kilobytes. And on the other hand, the JIT compiler, when 100 methods are compiled, at least in Ruby 2.7, when 100 methods are compiled, the total code size on Sinatra is usually 1 megabytes. So it's obviously larger than the size which CPU can efficiently cache. So compared to virtual machine, bytecode running on virtual machine, bytecode is shared between all the methods. So CPU doesn't need to cache a lot of code for running bytecodes, but native code needs to be cached for each method. So the more we compile the methods, the more the CPU cache become inefficient. So we need to. So the reason why we changed the default number from 1,000 to 100 was for that reason. But in the Ruby 3.0, I improved the mechanism to reduce the code size from 1 megabytes to about 250-ish kilobytes. So that's more, at least it's improved. And in Ruby 3.0 or master branch, in the Sinatra benchmark, it's doing a lot better than the 2.7, but still, because it consumes extra 250-ish kilobytes of the native code, it's a little bit slower than the non-JIT version, but we still have lots of places to be code size reducted. So if we share a lot more code in the native code between the multiple methods, we can reduce the code size further, and I hope that can fix the problem of the being slower in the JIT compiler.
So to follow up on that, and more for clarification than anything else, you're saying that one of the things that you're trying to play with here is you specifically want to fit all of this, everything that's JIT precompiled, right? You want to fit all that in L cache. And so if it's too big for L cache, we suddenly get a performance degradation, and we're just trying to fit underneath that line, more or less.
Yeah, kind of. Yeah, I think it's impossible to fit everything in cache, but at least we need to try. Major parts of the native code need to stay in the cache, at least for the hot path or very intensive parts.
Okay.
I'm going to embarrass myself here by talking about the stack, because I watched your talk and it talks about the difference between using the stack. So we were in a situation where the JIT, the JIT compiler works very well on the opt-caret, very good. But when you use it with Rails or Sinatra, then it's not as good. The latest release it's about the same, correct? It's kind of, and the memory usage is the same, CPU is the same, but we don't want the same. We want it to be faster.
Yep.
And one of the things you talk about is the stack. Now, being in the Ruby world, the stack is hidden from you. This is very much a kind of C thing. But my understanding of it is that in C, the variables on the stack are usually kept in registers. So if you can write an assembler program, a machine code program that only uses maybe 10 variables, and all of those 10 variables are kept in registers, it's going to be incredibly fast, maybe 20, 30 times faster than the nearest option. But obviously you can't just have 20 and 30 registers. You have to have more. So you have to reach out into memory to memory that's outside of this kind of short list of 10, 20 registers, correct?
Yep.
So opt-caret, because it doesn't use a lot of Ruby objects, is using variables which can be kept in the stack on those CPU registers, and therefore you get a very good performance increase with the JIT compiler. But Rails and Sinatra deals mainly with objects in Ruby, yes?
Yes.
The JIT compiler does not currently have a way of translating those objects into just registers. That's my very vague and flawed understanding of what's going on. But is that roughly the situation?
Partly correct and partly incorrect. So let me fix some wrong parts. So the first thing is, in opt-caret, we don't keep all the objects using opt-caret on stack, but instead we just have that in heap. So when we create an object in Ruby, we usually create an object in the Ruby heap slot, and we refer to that from, for example, from a hash reference or array reference, and therefore we don't need to keep it in stack, or we can't keep it in stack, because when we read from the virtual machine stack or machine stack, it's not guaranteed to be not referenced